Okay. So first, sorry, I want to apologize because on Monday I wrote down the date because I wanted to do special meeting. You guys can remember learning about the calculus, but I realize now that I just melted most people's brains instead. So I apologize for that. But don't worry, today's gonna be a lot more simple, a lot more fun, not as many crazy problems going on. So we're gonna jump into integration, which is something we've already been discussing, but we haven't used the terminology yet. Whenever we've taken, like, did the reverse derivative, the antiderivative, we just left it at that, and we didn't have a specific notation attached to it, like with the derivative. And when we were talking about area, we saw, this symbol mentioned, but didn't call it an integral. So now we're calling it what it is. This is an integral. This is a well, actually, I guess I should be specific. This is called a definite integral. And what we mean by definite integral is it has bounds. So that means that there's something there's definitely going to be something that's output from it, right? Whenever we're doing antiderivatives, typically, right, you have a plus c there, right? So there's like a infinite number of choices you can have for that. But this definite integral only gives you one particular choice. It may just be a number, it may be a function, but it's one thing. There's no plus c, no other options. It's just that, and so we call that that's a definite integral. Now, last time we talked about, I won't go over the proof again, but just to kind of outline our discussion, we kind of made a curve and considered kind of a function to represent the area, so that if I start at, I'll call this look big B or something. If I move over a distance, if I go to X, then I'm going to get the area essentially from B to X. And if I move it over here, then I would get the area from here to here. And what we noticed is that when we kind of understood what happens if I try to extend that and then study the derivative of the function a little bit, what ends up happening is we see that, so my function, so the top of this curve here is f of x. We get a very interesting result, and that's that the derivative of a of x is the function, right? So if I take the derivative of that area, that function for the area that gives me the area underneath the curve, that actually gives me the function itself. So this means that a of x is is an antiderivative right? We say there's all sorts of various options for antiderivatives, but a of x is one of them, right? So, and kind of going back to this notation here, we can actually write a of x as let's see, I'll put it over here. A of x. I want to actually, for now, it's just kind of an arbitrary, but if I want to write it in terms of in an actual integral form, it has a form, it goes from that big B I have on the left to so basically your lower bound to your upper which in this case is depending on whatever x is, of f of x dx. Okay, so that's our area in terms of integration, right? So we can kind of have a notation attached to it, know exactly what we're finding. But what we're finding from this is that the derivative of a is f of x, right? Which means that this, the book, I think the book uses. I didn't get to talk about it as much last time, but if you have, right, so I use x up here because I'm going to x is the right bound. So I can't put that in my function as well, because then I just have like conflicting, I have basically the variable I'm using in the bound as well, and it gets weird. So we can kind of use a dummy variable, just like when we were doing derivatives. It didn't, right, if I was doing derivative of x squared versus the derivative of t squared dx dt, it was the same process, it just was a different letter, right? And so it's the same thing here. But what we're going to see from this is that, again, f of t dt is going to be f of x, or some plus maybe some constant, right? It might be off, but it's the antiderivative of whatever f is, right? So what we took away from this, right, is that now let's consider that I have a couple of different values, right? So now we'll go back to my curve. And let's say that I have, so big B is still in place. It's just kind of a reference point of some sort. And let's say that I want to find the area from little a to little b, right? So kind of what we have up here. What I do, right, is first I look at, if I want to find the area between these two, right? Notice that we're not starting at big B, so I can't just use the area function initially, because uses that as its reference point. So what we want to look at first is I want to kind of separate, or not separate, I guess what I'm trying to say is, so if we look at this yellow area here, right, in corresponding to our area function, that's so that's a evaluated at a, right, because a is the point we're stopping at. I guess I'll write this in yellow so we can this is the same thing as the integral from b to a of f of t, right? And then I can do the same thing for b, right? So if I start at b, I'm getting the area from here to here. So I get the area of b equals the integral from big B to little b of f of t dt, right? So which of those two areas is bigger? Yeah, big B to little b, right? Because it goes a further distance, right? So if I want to find the area between just A and B, all I need to do is subtract those two areas, right? So I need to take big A at little a minus big A at little b, right? But we know, right, that our integral, right? So this is the same thing, so be able to write this below it. This is the same thing as the integral from big B to x of f of t dt, or from a. I'm fixing this all up, I'm sorry. This happens sometimes. I'm still learning, so a of b minus a of a. So we get little b in here minus from big B to a f of t t dt, right? But if we're finding the area between A and B here, right? This is of course still the same thing as just the integral from A to B of f of t dt, right? That's the notation we use to say if I want the area from one to another. That's what we use, just A to B of f of t dt, right? So finally, as a final connection point here, what's going to happen is we know that this is f of x plus c, and so this is going to be f of b plus c, right? Minus f of a plus c, right? F of that plus c, right? But the plus c's go away, so of course we're left with an equality that connects all this together, which says that again. Let's write it here. This integral is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. Okay. Good. This is the reason I take the time to kind of go through all of this, just because it is very important to at least have a little bit of a grip on an understanding of where it comes from, because that will just help you to continue to learn it, what they're growing in. Yeah. So yes, this is a definite integral, right? There's a definite. I've chosen this C I have is, I mean, it's what's going on here. Essentially, I mean, in what am I trying to say? Yes, in general, it should, if in the definite integral, it won't have a plus c, right? My whole purpose in showing the work is that, right, this is, no matter what the c is, will cancel out. And the c actually is there as a result of whatever that will be it, right? Because if I think about this formula in terms of that, I still get f of some b value, right? Which this is still some sort of constant, right? So that's what it is, a definite integral still. It may be confusing. Maybe I'll call this prime or something, so we know it's not just like your normal constant integration. It's the result of whatever that big B is. So, any other questions on that? That was a great question. No? Okay. Okay, examples. So this says that in order to find the area under a curve, I just find its antiderivative and then evaluate it with 2 points, right? So we'll go from 1 to 3 of 3x squared dx. Okay, so what I'm saying in this question is I want to find the area underneath 3x squared from 1 to 3. Okay, so in order to do this, what's the antiderivative of 3x squared? It'll be x cubed because it's 3 times x cubed over 3, which is just x cubed, right? So then this becomes, so it ends up being x cubed, which I will evaluate. Again, what I'm writing on the side is just, I have the antiderivative and then showing, I'm going to plug these two values in. So it's just kind of an intermediate step just to see what your antiderivative is for sure. So then we're going to get 3 to the third power minus 1 to the third power, which is what? 26. Good. See, is that hard? No, it's not that bad, right? It's an art, yeah, it's an arduous journey to get there, but it's not too bad, right? Let's do actually, no, that's well, actually I'll do that. Okay. Thought I'd do this one. We have to find the antiderivative, right? Yep. So how can I find the antiderivative of this piece? Good. So yeah, all right. Here f of x is 1/2 x to the negative 1/2, or that's the little f factor. Okay. Okay. So what's the antiderivative of that? Right. So we end up getting. So you get 1/2 times, and then this becomes x to the 1/2 over 1/2. But the 1/2 will just cancel. And then I integrate that from 1 to 3, or 1 to 4. Okay, what's the square root of 4? Two minus 1. 1. Thank you. Okay. Right, so all we did is we found the antiderivative, and then I plugged in my two values, my right endpoint, my left endpoint, subtracted the two, and I get 1. Okay, good. Yeah, no? Questions there? Comments, concerns? Please, if you have any questions, just I'm happy to if I need to slow down as well or something, I'm happy to do that too.
I got a question actually.
Yeah.
Are you taking that integral to the power of 4 then? What is that? The 4
Where?
to 1 subscripts? Yeah.
Here,
Yes.
that's just so what's happening here is, again, maybe I'll write it explicitly up here. This is the same thing as saying f of x. So when I write that, all that means is that I'm taking b and plugging it into f and a and plugging it into f. And then subtracting the two. That's all that means. I write it there. Like I said, if you have this already, it's not necessarily a necessary step, but it's just nice to see what your antiderivative is, and then you can plug it in there. Okay. How about, okay, let's do. Okay, what if I have something adding? What do we think? Is that changing? What is it? Nope, you just still find the antiderivative and then you plug in, right? So what's the antiderivative of my function in this case? Yeah. So yeah, 3 halves, 3x squared. Something to keep in mind, if you're wondering where the plus c's go, since we're working with definite integrals, they're not necessary, right? Because even if you decided to put a plus c on it, it would disappear anyway. Right, so it doesn't matter. And that's kind of what we were talking about earlier with the plus c's would cancel anyway. That's the whole point of the definite integral. Okay, so that's my antiderivative. Good. So that means that this is equal to, sorry, let me so we have x to the 4th over 4 plus 3x squared over 2, and then I take that from -1 to 1. Okay, so what do I get? What do I get when I plug in 1? Oh, you wouldn't have tried to combine it. I see. I'm gonna leave it just as 1/4 plus 3 halves minus, what do we get when I put -1 in there? Oh, what's gonna happen? Yeah, so if this seems weird, all that's happening in this case is, so the curve would probably look something of this sort, and if we're going from -1 to 1, what's happening is it's giving me this area over here, and it's giving me this area over here, but they're equal sizes, so they cancel out. You'll see that when you do it, you don't have to like remember that particular situation if you don't want to, but it does. Okay. Any other questions on that?
So it's like a negative area, like below a zero, it's just negative area, it's not a positive.
No, it would be represented by a negative. It'd be a negative number just because we're just interested to understand kind of the reference point, right? Because in this case, right, you kind of have everything, at least as far as we know, goes to the x-axis, right? So, or like it kind of collapses on that x-axis line. So obviously here, this curve's on top, right? But this one's saying, oh, I'm supposed to be on top, but I'm actually below, right? So that's why if it's below the graph, below the x-axis, it ends up being a negative area, which is a little, well, yeah, it's not too weird. It's just telling you where it's at, basically. The magnitude is still the same, like as it would make sense for the size of it. You just know it's below instead of above. Okay. Any other comments on that? You think you can do that pretty well? Okay. Of course, let me know if you have any questions, but so with that, we'll make some more examples. With that, we want to go ahead and keep moving on. So, let's see. So the next thing is we want to kind of get away from using the term antiderivative at this point. Because whenever we do antiderivatives, it's always associated with we want to associate with using this integral notation of sorts, right? Where I have that symbol, and then I'm going to have some function, right? But of course, we still are going to have situations where I don't pop out a plus c, right? Where I don't get a plus c out of it. Sorry, I got that backwards. Where we will get a plus c out of it, right? Because we don't want to just always do a definite integral. Sometimes it may be more useful to have, we just want to see what the antiderivative is supposed to be in the first place, right? Because as we're going to see, some functions are a little bit more difficult to and take the antiderivative of than just polynomials. And so we kind of want to have a general maybe grasp of what those look like. Okay, so if I don't put a bound on my integral, then we're just taking the antiderivative, right? And that's not plugging in any numbers, just the antiderivative. But in our more formal terms here, we're going to call this the integral. Okay, so the indefinite integral just has the f of x dx still, but it doesn't put any bounds. Because I just say, give me the antiderivative. I don't plug in any numbers in. Okay. Yeah, and with this, so we're still going to have a lot of the same rules, but now we can actually apply a symbol to it, right? If you remember before, we had to say if f of x was this, then big F of x was that, right? But now I can say the integral of x to the n dx is the same thing as x to the n plus 1 over n plus 1 c. Okay, so we've had this formula already, but now we're putting it in different terms. We're looking at it a bit differently, right? Because now we're looking at everything under this sort of integration umbrella rather than as just a random idea by itself. Yeah, I should mention as well, this part should look a little bit familiar to us, right? What if this was f prime, what would that be? It'd be dy, right? It's a differential, right? So the reason I say talking about differentials until this point is because that's kind of what goes inside the integral to represent each of the rectangles, right? Each rectangle is going to be represented by, and this generally we can just write f of x dx, right? But sometimes you know, you can, if you want to think about it that way, you're just going back to whatever f is and giving you that, but we'll leave it there for now. So x to the n dx is x to the n plus 1 over n plus 1 plus c. Let's see, we also had, I guess I'll put the silly example, but if I have a constant, I think it's k times d to the x, right? This is going to be c. Okay, and if I have, now I wrote k times x to the n in the antiderivative section, but we're going to be going a little bit beyond x to the n. So I'm going to write k times f of x. This is the same thing as k times the integral of f of x. So this works exactly the same way as derivatives do, right? If I have a constant times a function, I can just bring that constant outside the integral, right? It doesn't change anything. I can just move it outside and everything will work as expected, okay? So here are kind of our three basic first, rules that we want to use for doing these indefinite integrals where we are getting the antiderivative of these functions. Okay. Good. Any questions there? Should I do some examples? Okay, good. Okay. Someone give me a polynomial. Let's give us a polynomial. I don't know, just come up with one. Anybody got a fun one? No. Yes. I'll go. We'll do okay. So I want to find the integral of this thing. Okay. So, oh, actually, I might add another rule. I don't think the book actually lists this, but if I take the integral of u plus or minus b, then this is the same thing as the integral of u plus or minus the integral. That might be an important one for our purposes. So I can just take the integral of each individual one and add them up, right? So no longer do we have to say, oh, I have to do the antiderivative of this thing and then use it. I can just get kind of do the integral of each one separately, and then just add them together at the end. Okay, so I have two things adding here. So I'm going to do exactly that. I'm going to take this and I'm going to sum. Okay. How do I do this one? Any ideas? Okay. Right, so we're going to be using this x to the fourth. Can I do anything with this too? So that's the same thing as 1/2 times x to the fourth dx. Okay, that's actually, I'm gonna, as a quick aside here, right? I notice a lot of times that I might give like something of x and I might put it over a number. And then a lot of you guys are really trying to, worried about this number and trying to integrate it and fit it with everything to do the derivative, and then you use quotient rule, and then everything kind of gets a little crazy. If I have something over a number, I can just take that thing out as a fraction and then multiply by the function, right? So then it's just you can just have a constant times a function, right? You don't need to treat this as one function over another, right? If I have a constant at any time, just move it to the front, right? So just something to heed, because it would probably, I would probably help out a lot of you in those situations. Even on quiz 7, the problem I did in class was this one, and the problem that I gave on the quiz was this one. But there are several people that got tripped up because there was a 2 dividing, but that's just negative x squared over 2 is just negative 1/2 of x squared, right? So the derivative of that is just going to be negative 1/2 times 2x, right? No need to make it more complicated than it needs to be, right? Just remember how, multiplying, dividing with numbers works, right? Anytime I have a fraction, I can kind of move things around as I need to. Good, okay. So that's great. That'll be really easy to do then. That just goes with when my formula is done, right? What can I do with this one maybe to rewrite it? And so I can write this as what, x to what power? So negative 4th power. Awesome. So what is the integral of x to the 4th dx? Anybody? X to the 4th dx. Good. The integral of x to the negative 4th. Someone on this side. Awesome. Yeah. We just want to have a plus c on, right? Now I can take that and simplify it if I want to. I can write that as x to the 5th over 10 minus 2/3 x to the 3rd. Maybe minus 2 over 3x cubed, because I can move that back down. So that would be my answer.
Since you're splitting it up, would there technically be 2 seats there? Split it like that?
So yeah, that's the thing. Anytime you take the integral, the indefinite integral of anything, you're just gonna have 1 plus c at the end, right? Because you could have, you could be integrating like hundreds of functions altogether, right? And you're gonna have all sorts of plus c's, but in the end, they're just gonna add up to another constant. So there's no need to write them all separately, just put it all as one big one at the end. So yes, but technically you would think about it at each step that you said. Other questions, comments, concerns? Thoughts here. Okay. So really we've done this already. It's just a new code of paint, new kind of change the notation a little bit. You will want to adapt to this more because it's just easier to work with. So you can kind of have something easy to write down, so you're not just saying, oh, here's F and then here's little f and then here's big F, right? Like you have a kind of a transition point, something that moves it to that. Okay, cool. Okay, what could U substitution be about? Well, not all the time. Okay. U substitution. Okay. Someone do this for me. Oh man, I want to take the derivative of x squared plus 1 squared. Yeah, the derivative. I want someone else to. Okay, good. That's a great start. So bring the 2 in front. Okay. Right, the original. Yes. So I write down the original 2 minus 1, right? So we just get to the first power now. Good. What's the derivative of the inside? 2x. Good. This is good. You got it? What about the plus note? Okay, so this is the derivative of x squared plus 1, right? So now what if, so instead of taking the derivative of this thing, let's try to go backwards. I want to take the integral of this. Right? Clearly, we already know what's going to happen, right? It's going to turn into x squared plus 1 squared plus c. Right, but there's a little bit of careful consideration that's happening here, right? Because none of my formulas really work out as is, right? Like if I didn't know this, I couldn't just take this and say, oh yeah, of course it becomes that way, right? Because we have a couple things multiplying. I could pull things together and make it work out maybe a little easier, right? But right, we won't get that exact answer. So what do we do in this case? Well, what's going to happen, right? What we want to notice, right, is that, right? Remember, so what rule do we use to chain rule, right? The chain rule or the general power rule, right? So the general rule in this case, if I'm taking the derivative of u to the n power, right? Then I have nu to the n minus 1 times u over dx, right? So let's kind of take that perspective and look at what we have, right? So 2, well actually, yeah, the 2 is our n, right? X squared plus 1 is our u, and 1 is our n minus 1. 2x is our du over dx, right? So maybe let's replace what we have with those things, right? I'm going to get nu to the n minus 1 times du over dx times dx. What's going to happen to the dx's? They're going to cancel out. So this is the same thing as the integral of nu to the n minus 1 simply times du. Right? Can I do that one? You want to see with like x's and sort of thing? Well, it's probably easier to try to keep it as is. Remember, like if I have x to a power, right? And I want to take, so did I already erase it again? Let's write this again. If I have x to the n dx, and this is going to be x to the n plus 1 over n plus 1 c, right? And as long as these variables match, it doesn't matter. Again, it's just a dummy variable in this case. So if I'm using u, it's going to work the same way, right? Also, this n is just a constant, so it's just kind of hanging out. It's gonna come out to the side, right? So this is the same thing as n times the integral of u to the n minus one d, right? So if I use this formula, I'm gonna get n, right, times, so it's u to the n plus one, so now it's gonna become u to the n, or n minus one, u to the n minus one plus one, which would just be u to the n, over n, right, and then plus c. The ends will cancel out, so you get u to the n plus c. Right, which in our case, right, remember that n is 2 and u is that x squared plus 1, which will give us what we want. Okay, we think is it's maybe starting to click a little bit, right? Now let's look at another example. Like this. Okay, so has some of the same pieces, but our main issue is that now even if I wanted to, I couldn't multiply the 2x inside, right? It's a square root. However, a similar process might be able to work out here, right? So in the last example, right, we said, okay, I'm gonna let this piece be x squared plus 1, right? So what is the derivative of u? 2x. It's 2x. Maybe even easier to see, right? If I take dx and multiply to both sides, I get that du is 2x dx. Right? Do we have 2x dx in our integral? Right here. Yeah, that's du. So this integral is the same thing as the integral of the square root of u du. Do I know how to do this one? Yes, no, maybe so. Everybody, any guesses? Do I know how to do this one? What is it?
U to the half power.
Yeah. So let's write this as u to the 1/2 power. Okay. Now, so what's the integral of that?
Three halves.
You do the 3 halves.
Over 3 halves.
Over 3 halves, good. Plus c. And then I can flip my 2/3, right? But what's u? Good. So my final answer is going to be 2/3 x squared plus 1 3 halves plus c. Okay. Now, if you don't trust me, I understand. Let's check it, right? So let's take the derivative of 2/3 x squared plus 1. So the plus c is just going to go away. Someone help me out with this. What's the derivative of 2/3 x squared plus 1 with 3 halves? Not to the 2x, right? So remember, if I have something, so what is this 2/3 here? It's constant. Good. So I can bring that to the outside. Okay. How do I take the derivative of something to a power? So I'm gonna bring the power down, so I get 2/3 times 3/2 times what? What do I write next?
The original.
The original thing. Good, general power rule, right? To what power now? 1/2, good. And then what do I multiply by? It's 2x, good. Now 2/3 times 3/2 is 1, right? So that's just gonna go away, right? And x squared plus 1 to the 1/2 is the square root of x plus 1, which is exactly what we started with. Okay, so at least for some of you, it's starting to click a little bit, right? So this is the whole idea of u substitution. It's saying, as it looks like right now, I can't do anything with it, but maybe there's a couple pieces that are related a little closer than I think, right? The fact that, right, because the fact here, we let this thing on the inside be x squared plus 1, and that was its derivative, right? So what ended up happening is that troublesome part on the outside just became a du, right? And then it was, we got square root of u, or u to the 1/2 du, which was a lot easier, right, to evaluate, right? So that's the whole idea of u substitution, right? I'll write the general formula for this again. We use it. If I have u to the n du, then this is going to be u to the n plus 1 over n plus 1, right? Plus c, right? But this is a bit more of a process that doesn't just have a direct formula attached to it, right? Because you're going to need to sort of recognize, okay, maybe I'll call this thing u, and and then that means that this might turn into du or might get filtered out in some way. So let's go ahead and do a couple of examples. Okay. Examples. So we have the integral, just the indefinite integral of x squared times the square root of x cubed. Square root again. Okay, so as it stands, I'm not sure how to do that, and right now we don't have any sort of product rule for integrals, unfortunately. So what are we to do? Well, we want to see if I can make some sort of substitution that's going to make this work out, right? So let's kind of take a look at what we have, right? Generally, the best place to start to look for kind of the main thing that you're going to be moving through everything is the one that's inside of something troublesome, right? Or like in this case, right, I have this x cubed plus 1 inside of a square root, or in the last couple, it was like x squared plus 1 inside of a square root or squared. That's kind of the place to start. Okay, so let's do that right now. I'm not going to say that you'll have some neat way to get it correct every time, but there's at least pointers and you can check and see if it works out, right? Because if it doesn't work initially, then you can always try to figure, to check something else and see if that works, right? So let's take that thing on the inside and let's let that be x cubed plus 4. Okay. Just as it gets right now, right? Now again, there's just based on what we have on the rest, there's a good reason to pick that. But here's you, right? What's the derivative of that going to be? 3x squared. But I would prefer to write this as du equals 3x squared. Yeah. Same thing, it's just in like a differential form, essentially. Okay. Do I have an x squared up there? Great. Do I have a 3 up there? Okay, that's a little bit of an issue. So, but it's just a number, right? Remember, if I just have a number, right, inside my integral, I can easily multiply things in, take them out. It doesn't matter. It's only if it's a function of x that I have to like keep it in or worry about it. So here's an idea, right? I noticed that I have x squared and dx, right? And so I want that piece. And everything that's not that piece, I'm going to kind of move over, right? So I'm going to take 3 and divide it from both sides. And so that's going to leave me with du over 3 equals x squared dx. Okay, so now I have x squared dx, and up there's x squared dx, right? So this integral is going to become, so again, we said u is x cubed plus 1, so I have the square root of u, and then x squared dx, we said was du divided by 3. So we get this. Okay, which that number, right, that 1/3 again is from our discussion earlier. I'm just going to pull that just all the way through. And so I just am left with square root of u du. And if I remember correctly, it's 11. So what is the integral of the square root of u du? What is it? Good. So 1/3 times u to the 3 over 2 over 3 over 2 plus c. Good. Which I can simplify a little bit. So I can write that. So we get 1/3 times 2/3 u 3/2 plus c. So then I get 2 9s here. But we don't want to leave it in terms of u, right? Because we didn't start with u, we started with x. We need ends of x. So what is u in our case? Good. So that would be our final answer. Yes.
Where'd the x squared go?
Where did the x squared go?
You got dx.
Um,
Dx equals the integral of square root of u du 3. I don't know how you, where'd the x squared go?
So these two integrals are equal, right? We said x squared dx was what? Du over 3. So instead of writing x squared dx, I wrote du over 3. So x squared dx is basically inside that du over 3. Okay. The x squared is there. It's just it kind of got sucked back in, right? I like to think about a lot when it comes to chain rule that you're basically taking something and kind of pulling it out like it. But whenever it comes to u substitution, you have to kind of suck that thing back in. Like you have to pull it back in. So okay. Good. I know we're out of time. I'm happy to go through another example. If we want to, or you can go ahead and leave. I don't mind.
Where's the d? I can't wrap my head around the du. I understand that it works out in the end, but I don't understand why that disappears.
Here.
Oh, on the outside of the integral.
Because du over 3 is also means 1 du over 3. And put on the outside of that.
Right, you're not asking about the third, right, you're at,
Oh, no, yeah, sorry, the next one down, yeah.
so just where the DU goes.
Yeah.
That's just kind of the nature of integration, right? Because, I mean, think about what's happening, right? So, we're basically taking a bunch of rectangles, right? And we're adding them together, right? So you have the length times the width, right? So what's being output is the area, right? So I don't need this anymore. It disappears, right? I mean, I don't have the square root of u either technically, right? It kind of transforms. So once I do that sum, essentially, it turns into something different, right? It's just the nature, when you're doing integral, you have to have du inside it, or dx, or whatever it is, but whenever this sign's gone, that shouldn't be there.
Boil down to find big and complicated portions, setting it equal to u. The derivative of that difficult portion would be seeing what we have to work with on that as it relates to dx or maybe half.
Yeah, so if I could, to break it down of what's happening here, is I'm saying, man, I can't do this right now. Let's see, what do I got? Okay, I have, let's see, we have x squared, we have x2 plus 1. Oh, well, I know that, was it? Right. Right, well, the constant doesn't really matter as much, right? Because again, that's pretty flexible, right? I mean, literally, I could have started this problem and did that. It wouldn't have changed anything, right? And then I would have had what I wanted, right? I just got it later, right? The 1/3 just came out later. But the idea is to say, okay, what do I got here? Okay, I see an x cubed, I see an x squared. I know the derivative of x cubed is x squared. So maybe I can relate those two together. And once you see this, right, once you kind of get your u and du figured out, then it kind of smushes down a little bit to something similar, right? Because you kind of realized where the like why this is here, because it came out of this guy. Yeah, absolutely. Yeah, I was just we were still answering questions. Okay, yeah. Another example. I'll do a definite one, maybe. Book has let's not do square root, though. There's so many square roots. I mean, I guess it's the hardest one, or it's just do. I know the square root. Integral from. So this is from the book. Negative square root of 6 to -1. Don't worry. I mean, that doesn't really affect much to the end. We have x dx over square root. Don't worry, by the way. There's no notes there afterwards. So as needed. 10 minus x squared. Okay. Right. So we have this, right? So now the process starts again, and when we're doing u substitution, I say, okay. Let's look for something that's a bit complicated. Maybe I can see if something's related, right? So I have the square root. That's always a big sign, right? And has x squared inside. I know the derivative of an x squared term should give me an x term. So there's probably a relation here, right? So that's exactly what I'm going to do. I'm going to say u is 10 minus x squared. So what would du be in this case? Negative 2x dx. Right? Everybody seen that good so far? Okay, good. Negative 2x dx, right? Now I don't have negative 2x dx, I have x dx. So I'll just divide the -2. This. Okay. Okay, now from here, when it comes to definite integrals, I think for the sake of now, I might talk about that. for now, we'll leave that until the end, okay? So I'm going to. Right, because if we're changing everything in terms of U, those bounds may not be the same thing, right? Because obviously, you know, if I'm working with U, the bounds, yeah, they will be. Okay, so, good. Now let's replace things, right? So we said that 10 minus x squared is U. And we said that x dx is du over -2. Right? And all that -2 is going to be. It's going to come out to the front. So that, okay. So again, we just substituted using the information we have, right? Okay. So, how should I rewrite that square root of U? Good. Integrate it for me, so on. Using the -1/2.
Over 1/2.
Good, awesome. U to the 1/2. Over 1/2. Okay, which is great. And then plus C, or well, actually, not plus C necessarily because we're integrating, right? Or we're doing a definite integral, which again, I'll come back to that. If you choose to leave that till the end, that's fine. Like you could just do the indefinite integral and then just plug in at the end. So this 1/2 and this 1/2 will cancel, even if you choose to kind of multiply by the reciprocal, it'll do the same. What's U in our case?
It's x squared.
Yeah, so we have -10 minus x squared to the 1/2. Okay, now that I'm back in x, now I can use my bounds again from negative the square root of 6 to 1. To -1. Good, so if I plug -1 into here, I get what? Was it? Right, so you get 10 minus -1 squared to the 1/2 minus, right, so this is big F of B, right? Big F of -1 minus, and we'll have big F of 10 minus negative square root of 6 squared to the 1/2. Right. Here. That. So then from here, it's just some evaluation, right? So 10 minus 1 gives us 9, right? So we have, so I'm moving up here. Equals negative, so -9 to the 1/2. And then minus is a plus. 10 minus 6, so 4. So we have -9 to the 1/2 plus 4 to the 1/2.
Well, I'm trying to figure out, if you square that, is that negative still?
No, the negative goes away, right? Because it's inside the parentheses. If it was outside, then it wouldn't be square. It wouldn't be square, but it's square with it. So you get 4. K squared of 9 is what? What is it? Okay, so we get -3, -3, and square root of 4. Okay. Okay. I understand that these sections are going to be, well, 4.3 shouldn't be too bad. 4.5 might be a little bit tougher, so I would just encourage you guys to spend. This is 4.5, yeah. So basically, this was 4.3, this was 4.4. 4.4 doesn't have any problems. And then 4.5 talks about some of the formulas that I wrote, but the big bulk of it is about this. Because you've already done those other ones before and iterated, so it introduces. Please, let me know if you have any questions. Yeah,
We know when to plug in the negative.
after everything has been done.
How do you
After,
plug those in exactly?
huh?
How do you know where to plug those in?
So remember, I plug them into X in each case, right? So I'm gonna have, right, so remember if I have, so after I evaluate the integral of f of x dx, then you get f, big F of x, right? And that's from A to B. So this is gonna be big F of B minus big F of A, right? So I took the -1, I plugged it in first, minus putting in the negative first.
Thanks.
Cool. Um, Great. Yeah, how are you guys? How are you guys feeling about this? It's a little tough, but it takes a bit to like get yourself trained on it, but it becomes second nature at a point because you can start to like buy it. Like I can see x cubed, x squared, it's gonna work. X squared x, it's gonna work. Right, and that's the basic principle. In this class, we don't get into doing integrals of sine, cosine, or anything with logs or e's. So that's not until Prop 2. So it's this is the farthest we go really with integrals. That was your question.
Yeah, if we, but we'll just do it calc 2.
Yeah, the only all we're learning at this point is applying integrals and just the various like types of integrals, not procedures necessarily, but like we're gonna be talking about improper integrals. We're gonna be talking about like, well, just like approximating, because we already did approximating, but they have better ways to do that. So we're going to talk about that as well. I'm moving a little bit faster than my schedule because I wouldn't be able to have more time to do things, but or more time. I guess I felt like with some of the later sections I would be rushing, and so it would be hard to.
What really helps me, what really helps me learn it is the examples. When you actually throw the numbers in there, it actually helps. Monday, you're right. I melted my brain because especially because I was through that Wednesday before you even learned what an antiderivative was.
It was right. No,
But doing the homework and then actually just pulling an antiderivative up. The way I look at an antiderivative is like you're looking at the second derivative and you need to take it back to the first derivative.
basically, yeah. You're moving up. Yeah, you're at like the second derivative.
Going back up.
You're gonna go back up. Yeah, exactly. Yep. The other reason I have to go through all the hard stuff is because there's an element of that that produces like more critical thinking, and you're like to help you guys, because I could do examples all the time, but you wouldn't really be able to do anything with that after you got done with this class.
Yeah.
So, all right, I'll be done then.